Yeah, it should be a better approximation of backward.
Okay.
Dynamic
So
pressure during.
now I will just repeat
Yeah.
what I did.
Oh, really? Wait, I'm trying to think of.
I'm gonna do the for loop again. Implication factor. Now I have two different matrices. A different matrix. The first term is now it's 1.5 minus this. The second one is minus 0.5 divided by 1.5 minus that, right? Okay. And.
So all that dry.
Did you get the same thing?
I just stopped after
I
you
mean,
did
mostly
that.
just our rocket disintegrates in a puddle of melted
I was just
aluminum.
replacing the
When the stagnation temperature level up to shock temperature, shock heating is higher than the melting point of aluminum.
Okay,
and
so
you're there for
so
3
they are still
minutes.
deriving the amplification factor. Can you guys explain to the class what did you do to derive these numbers, derive the scheme?
Yeah, so we just guessed, like, okay, let's add another order. So we said, so if we need to like add another order, we need to have another point in there.
Another point here, right? So basically you have un here, you want du dt at also this point. So backward Euler only uses these 2 points. And you are saying, okay, I want to add one more point here, right? So the scheme would be du dt would be approximately equal to something over delta t that involves a times un plus b times un minus 1 plus c times un minus 2, right? I think these are exactly copied from your formula. Okay, and then what's the next step? Taylor series expansion, right? And where do you expand it?
UN,
Un. Why?
because that's where you care what du dt is.
Because if you expand it anywhere, the derivatives at that point is going to come out. Here you want derivative at un, right? So at n. That's why it's a good idea to expand over here. So basically un is equal to un minus 1 is going to be un minus delta t times du dt at n plus half delta t d square u dt square plus blah blah, right? And un minus 2 is going to be, here you only want to cancel these two terms, so I'm only going to expand over here. So you have this plus actually 2 times delta t square d square u dt square plus dot dot dot. Now you have a multiplied by this, b multiplied by this, a b, sorry, not a b, b and c and b and c. You add all of them together. You want to cancel this term, you want this term to be just a 1 and this term to be 0, right? Question?
So in the expression for un minus 2, where does the factor 2 come from?
Here? The factor 2, yeah, it's a good question. The factor 2 comes out of the Taylor series expansion. So Taylor series says that u at any point t can be expanded as u at another point t. Let's say this is t1, this is t0, plus t1 minus t0 times du dt at t0.
You can make it un plus 1, un minus 1, because we wouldn't propagate it minus 2.
That's a good point.
That's why I did the un plus 1, un minus 1. I just have to change sign plus 1 because I did it. That would be the same numbers.
Right, so if you do that, do you actually get the same thing?
Because we got the same.
The derivative at un plus 1 instead of un.
Right. So okay. So let me. Does everybody understand their different option of doing this? So they're saying if you do n plus 1 and n minus 1, it's easier because you never have to encounter this 2 delta t. But then you also have to, I think, expand what you want to approximate.
Yeah, I did that.
Okay, right. So basically you are expanding one more terms than I did, but like all your expansion is a little bit simpler, right? So that's a very that's a good alternative, right? In general, I'm going to talk the next scheme I'm going to talk about. Actually, you have to do that to analyze the order of accuracy, right? So okay, let's hold on your approach for a little bit. Of maybe somebody, I have a question of how do I expand DUDT at a different time point, right? Because it's not that obvious. So we'll discuss that a little bit later. Okay, so then basically you have three linear equations you want to solve for A, B, and C, and you come out with the scheme. So now let's look at the amplification factor for that scheme. And I'm just going to redo the surf to here. All right. So this is your actual amplification factor. So look at over here, it's a more straight, right, than that curved line of backward Euler or forward Euler. So what you see is that when you zoom into here, when you're using a very, very small delta t, the stability region of this scheme looks more like the stability region of an actual ODE, which is a straight line with zero curvature over here. All right, so this is basically the stability region of this scheme, which usually when you have a scheme that is accurate, easy to implement, which this is pretty easy to implement, and also have a pretty good stability region like this one, it usually has a name, right? This one, this particular scheme, which is not this one, this is called the BDF2. It's called the backward difference formula 2 because it's one is second order and two it involves two previous time step solutions, right? And there are other things like BDF3 and things like that. All right. So schemes like this is called a multi-step scheme because it involves like multiple steps as opposed to, let's say, backward Euler or forward Euler, which are single step schemes. Okay.